Welcome again to another physics class, and this is lesson 2. In our last lesson, we stopped on various examples of derived quantities. And the last one we mentioned which is number 6, is work. And then we said the formula for work is force multiplied by distance. And the first unit we may mention by then is joule, which is J. Now, to get other unit of work and get the number of units that work can take, we need to express this formula further because work is a derived quantity. Now, don't forget we treated force in the last lesson, and force will be equal to ma, then multiplied by d. Now, since we are dealing with derived quantities, and I told you when you want to get the number of quantity that any derived quantity contains, you need to reduce that derived quantity to its fundamental level. Now you can now say that acceleration is not fundamental, it's a derived quantity. So you need to reduce it further by saying acceleration will be equal to mv over t multiplied by d, because acceleration is what? Velocity over time taken. Therefore, velocity also is a derived. We can now reduce it now. M dd over tt, because velocity is also what? Displacement over time taken. Now, from what I have written now, as I explained in the last lesson, you can now say that all these quantities now, from this point, they are all fundamental. Mass is fundamental, displacement is fundamental, distance is fundamental, and tt is fundamental. So from there now, number first we are going to look at is number of quantities. Let's count it together. 1, 2, 3, 4, 5. It means the number of quantities that work contained is 5 quantity. 5 quantities. Now to get another unit now, from here, now from this formula, that is force multiplied by distance, we can see have another unit, which is unit number 2. The unit for force is Newton, while for distance is what? Meter. So you can have Newton meter as unit of work. Again, from this our expression, so this one will now give us md square over t square. Mind you, distance and displacement, as I told you in the last lesson, both were fundamental quantities. So they will take the unit of length, which is meter. So let's write the next unit now. Then this one will now be number 3, joule. Kilogram for mass, meter for d, and time, that is meter per second, meter square per second square, meter square per second square. Don't forget, now you can now see that from this md square t square, the unit of work can also be kilogram, meter square per second square. And the number of quantities that we can see from work is 5 quantities. Now, from this series of units of work that we have seen now, you can now say work can take 3 units, which are joule, Newton meter, kilogram, meter square per second square. All these ones are necessary purposely because of objective question. For instance now, if the question says all the following are the unit of work, except, it will now give you one wrong answer, as I said in the last lesson. then you should be able to identify these 3 units of work correctly. I know the one which will be the wrong answer. That is for work. Now, the next one now is surface tension, which we number. Now, the next one is moment of force. Moment of force. Now, sorry, is moment of force. We have done surface tension the last class. Moment of force. Moment of force. Now, moment of force, the formula for moment of force is force multiplied by perpendicular distance. Perpendicular distance. Mind you, when you say work, the distance here is horizontal distance, while for moment of force, its own distance is perpendicular distance. But mind you, distance is distance. They will still take the same unit. Now, from this one now, from what we have done on the board, if we agree together that perpendicular distance and horizontal distance will take the same unit, so we can now say F multiplied by D. Now the first unit of moment of force is 1 Newton meter. Now, to know the number of quantity that moment of force also contain, we need to express further as that of work. Without any argument, since this is force, this is distance, without wasting our time now, you can now say that everything we've done for work, right from this point, will be equal to that of moment of force also. Look at it. Force times distance, force times distance. Everything will be equal. If we agree that they be equal, then the next unit for moment of force also from this point will be equal to, which is number 2, kilogram meter square per second square. Kilogram meter square per second square. And the number of units also that moment of force, and the number of quantities that moment of force can also take will be 5. Now, note this one. You can now say that both work and moment of force can take the same unit. Look at it. But the only unit that differentiates between work and moment of force is joule. Moment of force cannot take joule as its own unit, but the other 2 units, they are the same. Therefore, now in an objective question can be given to you as, which of the following physical quantity can take the same unit as work? Which of the following physical quantity can take the same unit as work? Moment of force will be there, and it will now give you another other 3 wrong answer. But mind you, the correct answer, the only unit that can still take, the only quantity that can still take the same unit as work is what? Moment of force, from what we have seen on the board. Next example is stress. Stress. The formula for stress is force over area. And from what we have seen on the board, force is Newton, area is meter square. So the first unit of stress can be Newton per meter square. Newton per meter square. Next, let's express further. Force over area. To get the number of quantities that this one can contain, now we need to reduce all these derived quantity to their fundamental level. First is MA, MA over length times breadth. A is still derived, so it will give us MV over LBT, because don't forget, acceleration is velocity over time taken. Velocity is still derived. Then we are going to have md over lbtt. And from this one, we can now have md over lbt squared. Now, if we count the number of quantity now that stress contain, it will be 1, 2, 3, 4, 5, 6. That will be 6 quantities. 6 quantities. Now, to get the next unit for stress, let's come here. Mass for kilogram. This one, meter. Then, over meter again. That is m squared, because L is meter, B is meter. Then, S squared. So this one will now be, the next unit will be kilogram per meter per second squared. Kilogram per meter per second squared. Don't forget, as I said in the last lesson, now if the question asks you now to write the unit of stress from the basic quantity, it will be kilogram per meter per second squared. The unit from basic quantity or fundamental quantities, it will be kilogram per meter per second squared. That is what forms the basic quantity here is kilogram, meter, and second. You now see that all those units are from fundamental quantities. So the unit of stress from basic quantity is kilogram per meter per second squared. And the number of units, as I said, is 6. Now, let's continue to the next example, which is number 9. Number 9, let's take pressure. Pressure. For pressure, the formula also is force over area. Force over area. Now, from what I said, under work and moment of force, we now quickly discover that stress and pressure can take the same unit. But the first unit for pressure is Pascal. Pascal. While the next unit will be taken from this formula, which will be Newton per meter squared. Newton per meter squared. So without wasting our time now, you can now say that if we spread this force over area further, like that of stress, we are going to have the same thing. So to not waste our time, we can now quickly say that the next unit of pressure, which will be number 3 unit, will be kilogram per meter per second squared. As I said, under stress now, you can now say that the number of quantities that pressure can take will now be 1, 2, as in the case of stress, will now be 6 quantities. 6 quantity. The expression here is the same thing as for pressure. That is why we don't need to waste our time. So once you can know that of stress, definitely that of pressure will come out. But the only thing that is different is stress cannot take Pascal as its own unit, while the unit that differentiates them is Pascal. It is only pressure that can take Pascal as its own unit. Note that for because of objective question also. Now, let's move to another example. Which will be example 10. Example 10. Call it Young modulus. Modulus. Young modulus. Now, what is the formula of Young modulus? Young modulus is tensile stress over tensile strain. You can now see that both tensile stress and tensile strain are derived quantity. So as we have been doing, we need to reduce this one also to their fundamental level so that we can know the exact unit of Young modulus and the number of quantity that Young modulus can take. And at the same time, we will be able to write the basic unit of Young modulus from fundamental level. Now, stress, don't forget what we call tensile stress here is the same thing as stress here or tensile strain. So the formula for tensile strain as on the board will be force over area. But for strain, that will be divided by the formula for strain is extension over original length. Extension over original length. Or you call it new length over original length, E over L naught. So to express further, we are going to have F over A multiplied by L naught over E. Mind you, we can now have MA over LB multiplied by L naught over E. Now, if we express further from this point, we are going to have A is derived. We are going to have MV L naught over LB ET. Don't forget, our solution is what? Velocity over time taken. Velocity is still derived. Let's express further. Then it will now give us M d L naught over L B A T T. Now, from what is on the board now, here now we can get the exact number of quantities that Young modulus can take. Now count it. 1, 2, 3, 4, 5, 6, 7, 8. That will be 8 quantities. 8 quantities. 8 quantities. Now, to write the unit of Young modulus now, let's write the unit out now. The possible unit for Young modulus. The first one, let's look at it from this angle. F over A, E over L naught. This one will be meter. That one will cancel out. And what are we left with? It will be F over A. Then the first unit of Young modulus will be Newton per meter square. Once meter for this one over meter for this one, we cancel each other. We are now left with F over A. Now, let's continue. I have another unit. If you come here again, let's write the unit from this place and see those quantities that I can cancel. This one will be kilogram, meter over meter, another meter into second square. Therefore, you are going to have this one, we cancel this one. So we are going to have kilogram per meter per second square. Kilogram per meter per second square. Kilogram per meter per second square. So you can now say that Young modulus also can take the same unit as stress, pressure as on the board. And the units that join them together are Newton per meter and kilogram per meter per second square. Therefore, we can now conclude that both stress, pressure, Young modulus will have the same basic unit. Don't forget, both pressure, stress, and Young modulus we have the same basic unit. What is that basic unit? That is kilogram, meter, and second. That's the unit that form their basic unit. The next example, which is number 11, is momentum. 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 The formula for momentum is mass multiplied by velocity. Now, from this formula now, the first unit that we can arrive at is, we know the unit of mass is kilogram. The unit of velocity is meter per second. So it will be kilogram meter per second. Kilogram meter per second. Now, to know the number of units, see, maybe we can still have another unit for momentum. Let's express further. That will be mass multiplied by distance over time taken. Mass multiplied by distance over time taken, that is, or displacement over time taken, that is, velocity is what? Displacement over time taken. So from there now, mass is fundamental, displacement is fundamental, time is fundamental. It means if you write the unit here now from this place also, kilogram for mass, then meter for displacement, per second for time. So we are still going to have the same unit, and that will be the basic unit of momentum. Now, what is the number of quantities now? 1, 2, 3, making three quantities. Three quantities. Three quantities. That's number 11 example. Let's take another example. And the next example will be number 12, which is impulse. Impulse. Impulse, the formula is force multiplied by time taken. Force multiplied by time taken. Now, from the formula on the board, the first unit will be Newton seconds. Newton seconds. Newton for force, second for time. Let's express further. Maybe we are still going to have another unit. Now, force is MA multiplied by T. A is derived. Express further, it will give M into V over T multiplied by T. Again, velocity is derived. It will be M dt over tt. Therefore, one we go away, that M d over t. You can now look at it, the same thing as momentum. Therefore, we can now say another unit for impulse can be kilogram meter per second. That is number 2 unit. Kilogram meter per second. It means momentum and impulse also can take the same unit. And the unit that join them together is kilogram meter per second. So also, their basic unit, the same thing, kilogram meter per second. But at the same time, what the number of quantities that impulse can take? From here, it is 3 quantity also. Now, the next thing is the next example, which will form example 13, is power. Power. Power, the formula of power is energy transfer. Energy transfer over time taken. Or you say work done, work done, work done, work done over time taken. Now, if it is work done over time taken or energy over time taken, then the first unit we can have for power is 1 Pascal. Pascal. Now, sorry, Pascal is for pressure, as I said the other time. The first unit is watt. Watt. Now, that's the first unit. Again, from this formula, energy transfer over time taken or work done, then it can be number 2, joule per second. That's another unit of power. Now let's express further and see, maybe we can have another unit and get the number of quantities for power. So it can be work is force times distance, then over time taken. Then it will be equal to MAD over time taken. It will be equal to MVD over TT. V, velocity, is still derived. That will be MDD over TTT. Now, from there now, all these one are fundamental. Then we can now get the number of quantity for power, which is how many quantities now? 6, making 6 quantities. To get the next unit now for power, let's write it. Mass, kilogram, meter, that's meter square. TTT, that's per second cube. It means the next unit of power can be kilogram meter square per second cube. Kilogram meter square per second cube. Again, let's reverse a little bit to have another unit for power. Let's come here. Here, this is Newton, this is meter, this is second. Then the next unit for power can be Newton meter per second. From FD over T, Newton meter per second. Making how many units for power now? 4. So we have this 4 units. But the unit from the basic quantities is kilogram meter square per second cube. So if the question asks you again to write the unit of power from the basic level, it will be kilogram meter square per second cube. Now, let's have one more example before we stop for today. But don't forget to subscribe, for more learning. Number 14, electromotive force. In short, we call it EMF, electromotive force. The formula for electromotive force is work done over quantity of charge. Work done over quantity of charge, which is equal to W over Q. We always come across work. So the formula for work will be F multiplied by D, and that of quantity of charge is current multiplied by time. Now, to express further, we can still express this one further, but let's write the unit now. The common unit we know for electromotive force in physics is volts. Now, from this formula, we can still have another unit. That will be number 2. Work is joule. Quantity of charge is coulomb. So it will be joule per coulomb. Now, if we express further, before we write over T, let's say over Q. It means from this point, we can have another unit for electromotive force. What that will be Newton meter per coulomb. Please don't forget all these formula. They are very, very important because we can be given any question under it. Let's express further and have another unit and know the number of quantities that this electromotive force can take. So from there we can now say F multiplied by D, that is NAD. Then if you say over Q again, then we can see have another unit. Mind you, this one will be kilogram. Velocity is meter per second square. This is another meter. So we are going to have number 4, kilogram meter square per second square per coulomb. That is another unit from this point. Kilogram for mass. Acceleration is what? Meter per second square. Then this is another meter. That will be meter square. It will be kilogram meter per second square per coulomb. Kilogram meter square per second square per coulomb. Let's express further. So it will now give us. Now, let's come back here. We can see have another unit because this one will be F D over IT. F D over IT. Now from there, this one will be Newton. This one will be meter. That's another unit, number 5. Newton meter per ampere. That is per second. Newton meter per ampere per second. That's what I said the other time. The number of units that you can have for any derived quantity depend on the fundamental quantities that such derived quantity can take. You cannot say that the number of fundamental quantities that electromotive force can take, there are many. That is why we have multiple units of electromotive force. So let's express further. As I said, from here now, this one will now be MAD over IT. We've written formula for that, for unit for that one. Let's express further. Then we now give us MVD over LITT. velocity is still derived. Let's express it further. That will be md over I t. Now from here now, you can now see that all quantities here are fundamental. No derived quantity again. Then from there we can now get the number of quantity that electromotive force can take. Let's count it together. This is 3, this is 4. Making how many quantities? 7 quantities. 7 quantities. Now, from here now, if you want to write another unit for electromotive force, this one now can be, that's number 6, kilogram meter square per ampere, then per second cube. Kilogram meter square per ampere per second cube. Now, finally, you can now say that the basic unit of electromotive force is this, the last one. If you check all these units now, no derived units there at all. All are fundamental units. Compared to this one, the only derived unit we have here is coulomb. That is the unit of quantity of charge. So it's a derived. But here, there's no derived at all. All are fundamental quantity. That is why we should agree that the basic unit of electromotive force is this last one, which is kilogram meter square per ampere per cube, per second cube. Now, today again, you can see that we've looked at other examples of derived quantities and their derivation of formula, unit, and number of quantity that each can take. But as I said in the beginning, there are many derived quantities, but time will not permit us to write all the derived quantities here. But from the list that we have written, you can now see that if you are given any question on derived quantity, analyze the question like this. You should be able to answer any question under it. But if you still have any question, either on this topic or in any topic in physics, you can send your question, ask your question through the comment section or through the WhatsApp link in the channel. Thank you.